Hello, fellow problem solvers. So they're going to be doing a problem from the British Math Olympiad 2013, round 2, problem number 2. The reason I'm doing the British Math Olympiad round 2 is because somebody who watches this channel commented that they were going on the British Math Olympiad, and I decided, hey, let me try to do some problems that were in previous British Math Olympiads. So this is a lovely geometry problem. I invite you to try it out for a minimum of 15 minutes, ideally 45 minutes to an hour, not more than 2.5 hours. If you'd like to go along with us, give it a go. Draw the diagram, put your first ideas out on paper for the next 10 minutes. So this type of geometry problem I like. I think this is familiar to me. I haven't actually seen the problem before making this video, but I know roughly the difficulty here. So we have a triangle ABC. Okay, let's draw this triangle ABC. Our first diagram is not going to be very good because we want to see what's actually happening in the problem, and then we can draw a second diagram that's much better. So ABP is PCA. So ABP is ACP. So if I draw one here, it's like a meeting of heights, but I've made it a meeting of heights just to make sure it doesn't have anything to do with heights. Let's make it like this. Okay, so this is X and this is X. That's point P, and Q is such that PBQC is a parallelogram. So it's a symmetric point here, Q, and we must prove that QAB is equal to CAP. Wait, so when this... Oh, okay. So when this is in fact the orthocenter, this ends up being that orthocenter lemma. Like once you reflect orthocenter over the midpoint. Okay, so how are we ever going to do this? You know, this is a phenomenal problem for a lemma that I know. I think it will be a phenomenal problem for a lemma. Yeah, QAB and PAC. Okay, so how do we go about this? Well, let's think. So there are many ways to go about this problem. One thing immediately for me is like, how do I use the fact that this angle is equal to this angle and that we have a parallelogram? Like there's these two conditions, right, that we have to use. So first, let's draw another picture. Now that I know where P is, I'll draw a picture that's this. Okay, that's nicer. This is P, and here's Q. This is X, and this is X. A, B, C. And now, my thinking, there's one line of thinking which says, let me use the fact that this is X and connect that this is X as well. How can I ever do that? Right, this is beta minus X, gamma minus X, but how am I getting anywhere from there? When I calculate the angles here, I have gamma minus X, so the whole thing is beta plus gamma minus X. And this is beta minus X, so this angle and this angle are equal. Oh, that's actually quite nice. I was just talking about how these angles are equal, and it's like, yeah, actually, that's not too bad. But how else can we use this condition? So we have this is equal to this, and we need to prove that PAB and QAC are identical. So let's see this angle PAB. Mind you, the converse is identical. Is identical, right? If we're CAP is BAQ. It's the same thing, right? Because PAQ is shared. So here, what would you do? Here's where I invite you to pause for 10 minutes and come up with the ideas on how you can maybe connect these two angles, right? Pause now. And here's one idea. One idea is to make another parallelogram. Now, one obvious question is why? So one reason why is because I saw something like this before, right? Geometry is a field where when you saw other tricks and tips, things that people do in geometry problems, then you can try to use those same tips and tricks on other problems. Here, why I want to connect it is because, well, I think it's a good connector is because if I make a parallelogram right here, call this point R, such that RA is parallel to PC, and RP is parallel to RP is parallel to AC. Why do I want to make this a parallelogram? Well, I take advantage of the fact that this is X. That's one thing. I also now have these points are concyclic, BPAR. That is the main reason why I'm making it a parallelogram. Furthermore, might there be something else here in this picture that I can connect? Also, mind you, I now have the angle PAC is equal to the angle RPA is equal to RBA. Right, so I have this angle. Now, is there anything else I might have? Now, I invite you here to pause for 15 minutes and push the problem further. And here's the next step. So I have this as X, and let's call this angle Z. Z, I have this as Z. Right. What else do I have from the fact that this is a parallelogram, mind you? I'm also making a parallelogram for another reason. And the reason is that a parallelogram is a parallelogram if this is parallel to this, and this is equal to this. That's also a condition for a parallelogram, a sufficient and necessary one. And how you can prove this, you have two lines which are identical in length. You cross them, these are parallel to each other. Now you have all the angles, right? You have this angle is equal to this angle, this one to this one, this shared angle. You have the sides which are equal, so you have here, you have congruency. And now that you have congruence, you have this is equal to this is equal to this. And now you can use, again, now you can use side, angle, side between these two triangles and get this is equal to this, and then you have their parallel, right? It's a rule of thumb. It might sound impressive if you haven't done a lot of geometry before, but trust me, the more geometry you do, these sorts of things become natural. These are sort of rules of thumb that you see. It's instead of taking 1, 2, 3 steps, because I've taken those 3 steps, like I've done this 10, 20 times, now I just see, oh, these identical and parallel, parallelogram, right? That's sort of how these things work. Now here, this is parallel and equal to this, is parallel and equal to this. So I also have, if RACP is a parallelogram, then also that implies that RAQB is a parallelogram. And that's one thing. One thing is that it is freaking cool that you just have a parallelogram, boom, boom, boom. And now this implies that the angle QAB is equal, so QAB is equal to RBA, and now we know that, and now we're done, because RBA is equal to the angle RPA, which is equal to the angle BAC, so QAB is BAC, and then that also follows, oh yeah, that's what we need to prove. We need to prove QAB and BAC. And that proves these things are equal. And now the problem is solved. I suspected it was this type of problem when I saw it, but yeah, and it is. It's a very, very cool trick. When I saw this the first time, I was doing some synthetic geometry handout. I saw this and I was like, whoa, that thing just like boom, 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 done. It's amazing. And it has the logic, the motivating factor here is, sure, you're translating this angle here, but the big motivation is this is X. I'll make a parallelogram here, and I'll have X, and X, I'll have concyclic points. I'll have two things which don't always hold true for any point P. And I'll have two things instead of one. I'll add a thing, and then I'll have another thing which is also cool. And in fact, I don't have just one thing. I have two new things. I have concyclic and I have a parallelogram. And that here is enough to solve the problem. Now, another way this same problem could have been solved, I believe, is by using a lemma. A lemma that is frequently can be very, very useful in geometry, and that is that if sine of alpha minus x over sine of x is equal to sine of alpha minus z over sine of z. This implies that x is equal to z, assuming x and z are both between 0 and alpha. Right? You can prove this by cross multiplication. You can prove this by similar triangles. I invite you to try to prove that yourself. And here, why would that be cool? Well, we have beta minus x, and then this angle is gamma minus x. Now this one is gamma minus x, beta minus x. What we want to prove is that the sine of PAC over the sine of the angle PAB is equal to the sine of the angle QAB over the sine of the angle QAC. That is, now, if I was just writing a solution and I told you, and I said, we're going to prove this because of this, you would think it's out of nowhere, but for me, it's out of somewhere because I know this lemma. Furthermore, I have an alpha here. And thirdly, I know that I'm going, when I have the signs here, like the sign of PAB, I'll use x, I'll get rid of AP. When I use sign of this over sign of this, I'll use x, get rid of AP, and I'll have BP over CP. Like, are you kidding me? And then when I have BP over CP, I'll also have that when I use the signs here of QAC. And really, this finishes the problem immediately. Like, I'm only seeing it now, like it's even faster than I thought it would be. So what is this angle? The sine of PAC. So we can calculate it as the sine of the angle PAC over sine of, actually is equal to sine of x times what? So what do we have? PAC, we're going to have BP over AP. Right. So this is what we have to prove. We know that this is equal to, when we multiply and divide, this is going to be BP over CP. The x's cancel out and the AP's cancel out. Now what about, actually what is, yeah, PAC. Oh, wait a second, this is, this actually is PAC. So if it's PAC, then it's CP over BP. So here we have CP over BP. And then what do we have here? It's a very similar thing. We're going to use the signs of QAC and QAB. Which angle are we going to use? Well, the ABQ, ACQ, because they're equal and because the AQ cancels out. And then we get the sine of the angle QAB is going to be equal to what? QAB, what do we have? We have, this is then sine of QAB is equal to the sine of beta plus gamma minus x. That's the sine of this angle right here. And now it's this times QAB, we have BQ over AQ. And then when you multiply and divide these, you'll get that this thing right here is equal to BQ because these signs cancel out. AQ cancels out, so this will be BQ over CQ. Because BPCQ is a parallelogram, these two things are equal because CP is equal to BQ, BP is equal to CQ. You can even say due to similarity of these two triangles. Do you even need it's a parallelogram? Yeah, you need similarity on one hand, and you need this angle to be equal to this angle. And I think that sort of, actually, you don't need similarity. You need this over this to be equal to this over this, and you need the same angle. Though that might uniquely define point Q. I'm actually not sure. I think it might. It's difficult to tell, but it doesn't matter because we've solved the problem. It's the second problem in round 2 on the British Math Olympiad in 2013. A nice geometry problem. I really, really, really like this sort of thing. This, make a parallelogram. And I've tried it in some problems. I think, has it ever worked? No. But another thing has worked, which is kind of similar, which is construct two triangles, which are a triangle that is similar to another triangle. That's also a thing I saw in some solutions, and it's amazing. It's worked once for me. And this finishes up the problem, and it's good to know these tricks. Actually, I have used this when I was doing a variant or a similar problem to this one. where it was just like a parallelogram and a parallelogram was constructed. And I was like, oh, okay, let me construct another one. And then I construct another one and I get 2. I get 2 for the price of 1. And I finish up the problem. This whole thing finishes up our problem, and as always, thanks for problem solving.